And then this is the bottom section. So for the top section, the area that we have to consider is this entire, we have to consider this area first. And then we have to add this area. Okay. So as we know, this is our flange. And these two are our webs. Okay. So in order to determine the shear stress at the centroid, this is our centroid. Okay. So we have to, what we have to do is first moment area about the z-axis. So this is my transformation. This is our y, this is our z. So this is equal to a y bar, right? So that's a general formula. So we have to do a y bar for the flange plus by the a y bar for the web. Okay. So when that's the case, we tend to do the width depth y bar. Okay. So the width is 160 for the flange. The depth is 20. And then the y bar is equal to what? The y bar is equal to 35 plus by 15 multiplied by half. Right. Then we are going to do the web plus. Okay. So the web is twice. The width is 20. The depth is 15. And then multiply by 15 and then multiply by another half. Okay. So this will be equal to 160 or 35 plus 15 times 0.5 times 20 times 160 is equal to 80 times 10 to the power 3 plus by 20 times 15 times 15 times 0.5 times 2 is equal to 4500. So this will be equal to 80 power 3 plus by 4500 is equal to 84.5 times 10 to the power 3 millimeter cube, or 84.5 times 10 to the power minus 6 meter cube. Okay. Now this is by considering the top. Okay, so you have to do addition of the flange, and likewise you have to do addition of the web. Now what will happen, right, if we apply using the bottom section, right? So if, now coming back to this rule, this theory over here, right? If the thickness is constant, so the thickness is constant over here, we are focusing on the web. Why we are focusing on the web? Because the centroid is in the web, right? So if we were to take either from the top or from the bottom, the first moment of area will be the same. I repeat again, the first moment of area should be the same. If it's wrong, something is wrong. Okay, so I'm going to consider the bottom section. So I'm just going to do on the side. So we are going to do tau centroid. Okay, by using the bottom section. The answer should be the same. Okay, so QZ is equal, so it's equal to a y bar, right? So the area, we got two areas left and right. The width is 20. The depth is, so 100 minus by 35, right? So 100 minus by 35 multiplied by 100 minus by 35 divided by half. So this will be equal to 65 times 65 times 0.5 times 20 times 2 is equal to 84.5 times 10 to the power 3 millimeter cube, or 84.5 times 10 to the power minus 6 meter cube. You can see that the answer is the what? Is the same. I repeat again, you can see that the answer is the what? The answer is the same. Yes or no? Whether you take it from the top or you take it from the bottom. And why is that? Because if you look at what we have derived over here, or what we have seen over here, if the cross section is what? Is constant. Whether you take it from the top or when you take it from the bottom, the answer will be and shall be the what? Shall be the same. Okay. If not, then yeah, we have to be worried. Okay. Right. So what I'm going to do now is we are going to I mean the most important thing for this course is the first moment of area. That's the most critical. Okay. So now what I'm going to do is we're going to do a full blown problem. Okay. So you have this. Okay. So and what to watch out for. Okay. What to be careful. Okay. So we have a structure like this. Okay. We have determined most of the term already, right? So I don't want you to underestimate how to determine the Vy, okay, or how to determine the shear force. A lot of times students make mistake by determining the shear force, unfortunately. Okay. So for the beam shown, consider section NN and determine the shear stress at point A, at point B, and we already have quite most of these values already. Okay, so we have to first look at the reaction at point A and point B. So now I start sketching the transformation. So I know for the fact this is my X and this is my Y and this is our rotation about the Z, right? And then over here there is a cross-section view, and this is the Y and this is the Z. Okay, so from here we can construct the free body diagram. First of all, we know that the formula we're going to apply is here. XY is equal to Vy over IZZ QZ over T, right? So the first thing we have to find is we have to determine what is our Vy. A lot of times students make mistake is that, okay, I have 180 times 10 to the power 3. My Vy is equal to what? 180 times 10 to the power 3, and that's wrong. That's outright wrong. And you'll see why. Okay. To solve this, we have to construct our free body diagram first. Okay, so we have to, before we have to find our reactions at point A and point B. Okay, so reaction at point A and point B, you can start by you doing static analysis. Okay, so when we do static analysis, we're going to do summation about moment about the z-axis at point A is equal to 0. So you have going in a clockwise direction, so it's minus 180 times 10 to the power 3 multiplied by a distance of 0.5, and then you have plus by by. Because why? Because you have a reaction at AY, and then you have a reaction at BY. Okay, so this is equal to 0. From here, BY is equal to 90 times 10. Okay, 90 times 10 to the power 3 Newton. When that's the case, the next thing again, static analysis, summation about forces in the y direction is equal to 0. So you have AY plus by BY minus by 180 times 10 to the power 3 is equal to 0. So for this case, your AY plus by 90 times 10 to the power 3 minus by 180. So from here, we have determined that our AY is equal to 19 times 10 to the power 3 meter. Okay. So from here, we can sketch our shear force diagram. Okay. So I incorporate this so we can sketch our shear force diagram. Right. And I hope you all still remember how to do your shear force and bending moment diagram. If not, don't worry, I will help you guys out. Okay. So this is our first line. And then we have our horizontal. And then this is our V. This is our 90. This is our minus 90. So we know that A to the center, right? So this is 0. This is 0.5. And over here is 1. We know that this looks like this. Okay, so this will go horizontal, right? Then at 0.5, due to the force of 180, it will get a negative 180 now, or negative 90 because of the 180 movement. And then go horizontal, and then you have a reaction at point B, pushing it back up to 0. So we know that this height over here, or the length over here, or the height over here, this is in fact our 180 times 10 to the power 3. So the outcome of this is what? So from here, we have determined, so from here, we found that what? From here, we found that Vy is equal to 90 times 10 to the power 3 Newton. And it's not equal to what? 180. So a lot of times when students see a problem like this, they are very quick to make judgment. Okay, it's going to be what? It's going to be 180. It's wrong. Okay, it's going to be 90. Okay, right. So what I'm going to do, I've not determined IZZ yet. I want to see, did I have a IZZ value? No, I've not determined IZZ value. Hold on. No. So what I'll do, I only have left 5 minutes. I'm going to stop here. So in order to find stresses at point A, point B, okay, we already know our what? We already know our first moment of area already. Okay, we already found what is our first moment of area that we have found over here, right? We found our first moment of area at point A. Okay, so it's a matter of just plugging in the formula. Okay. Again, today's learning objective is to determine the what? First moment of area, which is the most important thing. Okay. Second moment of area, all of you can do it very quickly by now. Okay. If that's the case, I'll see you guys next week on Tuesday. Okay. I'll still stay around if you have questions. Okay.